Today I'm going to give a presentation on introducing some new options for motion control using LabVIEW. I'm a newbie here, so please be kind. My first conference. So I'm Eric Schaffer, Schaffer Engineering, and I'm very happy to have joining me Ed Novak from Trio Motion Technology. He's the North American Sales Manager.
So today, just real quick, I just want to say that we want to show you something where we're going to be connecting things to LabVIEW, and we wanted to show you some options of what you can do with it, specifically with Trio controls. And Eric's got a nice setup here to show you what he's done. A little bit of a collaboration between Trio and Schaffer Engineering was to develop this toolkit to work with LabVIEW. And Eric's done a great job. And that's what we're going to show you here. And we'll talk about the products later on. We'll have the table up front, so answer questions when you get there. But we're going to let Eric take it off.
Okay, so how many people have done motion with LabVIEW previously? That's quite a few. How many are doing it now? Fewer. Okay, so that's basically what I'm giving this presentation about is a new method to do it that's actually going to be fairly simple or different methods, and some could be simple enough that people who've never done motion before can then feel comfortable doing motion with LabVIEW. So I'm going to give a little introduction about myself, talk about motion history with LabVIEW. I'm going to talk about some future options using the Trio controllers, some of those options. Then we're going to actually have Ed talk about some of the capabilities of these controllers. Then show some options using the controllers, using flags between LabVIEW to communicate and between a LabVIEW program and a program that's written on their software. Also, we'll show you how to use their ActiveX or any of their functions that exist. I'll give some demos there, then I'll introduce the Trio Motion Toolkit, which I developed, give demos there, and then talk a little bit about where to find that. So myself, I've been in motion for many years. I started out at a company called MTS Systems, that's in Eden Prairie, Minnesota. I was in their automation group for 16 years. I delivered over 150 projects involving motion at that time, and many of them used high-speed multi-axis synchronization. Once I started using LabVIEW, I've delivered over 50 axis of motion since 1994 using multiple of their products. So if anybody sort of goes back in history and sort of remembers what was LabVIEW motion. So it started out with flex motion. That was a PXI-based motion with a low-level programming capability. It's been obsolete for more than 10 years. And they decided to develop their own motion using what they called NI soft motion. It was a compact Rio-based. It, again, is no longer available from NI. Its last release of software was in 2018. And not only not supported by NI, you can't buy equipment from NI to support it now. So here I am delivering my motion to my customers, and NI informs me well ahead of time that this is going to come to an end. So what do? I said, well, I need to support my customers. So in back 2018, I first purchased some hardware because I need to create my own demo systems. And at that time, I was delivering motion with a local distributor called PowerMation using soft motion and looking for other partners. I talked to Galil and others. They suggested I talk to Trio. At that time, I actually got in contact with Ed. He lent me some equipment, and I was successfully able to develop some prototype systems, so I knew there was some potential in the future. So Trio Motion Technology, I know Ed can talk about this later, but they have been developing and providing controllers since the 1980s, and they are supported by many of your local vendors around the world, such as Paramation, which I worked with. And how we interact with their motion basically is they have an extreme set of ActiveX library that I can then use, or you can use, to run their functions. So here Ed can talk about, these are his stepper and analog controls.
Yeah, so we have a whole line of controls and then also dovetail into motors and drives. The controls are sort of broken up into a couple of groups, what we call conventional controls, which are what you see up here, and EtherCAT-based controls. I was going to have some more little show and tell, but apparently somebody in Minnesota needed my baggage be better than I did, and so I don't have any hardware with me to fondle with, but you can kind of get the idea. So these controllers you see here, we have one up here that's running. It's this little guy here, the 403. These are stepper and servo, analog servo controls. And they also have expanded I/O capability, which is what these CAN modules are. So what that gives you is a connection from LabVIEW into any of these devices that'll go up to 16 axes of stepper control for you. So you can offload potentially a lot of capability within the controller, take advantage of what it can do in terms of kinematics or advanced motion capability that you might want. On the flip side, we have EtherCAT-based controls. Starting with our most popular one, which is this little guy here, which is called a Flex X control. This will do up to 64 axes of control over EtherCAT. Servo cycles down to 125 microseconds. So it's a pretty capable little unit, very cost effective. It also has a whole family of snap-on I/O modules that go along with it. So you can bring encoders into the system, analog I/O, transducers, load cells, other signals you might want to bring into this system, as well as into LabVIEW. So the next one up is this slightly bigger model, just a bigger brother, same kind of capability, 64 axes. It's an MC6N. It's over here on that other top servo display. A new unit coming out right now is called our PCMCAT 2. So this is an IPC that's available to you that would be very advantageous in the LabVIEW world. It talks to our side of the control through a dedicated core of the processor through DPR. So you can get real-time data in and out of the controller very quickly through into the Windows environment, into LabVIEW. Very capable, of course. And then we have a 664, which is our top-end controller at the moment, which is up to 128 axes. So really, just kind of a platform from a couple, 3 axes up to 100-plus axes over EtherCAT, all talk to exactly the same way, same toolkit, same everything.
Okay. So using the Trio Motion, they have developed a software editor over the years. It's pretty good. They're using a basic style of programming. And then what we can do, or you can do, is in a LabVIEW program, interact between ActiveX flags and digital I/O. Alternatively, you can then use any of their ActiveX functions and write to them. They have a library that's useful, or any of their Trio basic functions, anything that's in there that they have is available to you. So I'm going to right now what I'm doing is I'm opening up their software manual. And if you see right here, there's over 1,300 pages.
You're still on that slide there, by the way.
Okay. So imagine you're looking at this manual of 1,300 pages of functions, any of which are hundreds and hundreds of functions. Any of those are available. And what's unique which I wish I could show you, is that they have what's called, and one of my favorite, the frame function. And they have preloaded in their controller multiple robotic designs that you can access and define what the robot looks like, and then the operator could just say, this is the endpoint I want to go to, and it can automatically control and run to those positions. So we will move on, but that's all I was going to show you is part of their manual here. Okay, so what I'm going to demo here first is how can we do that running a basic program and interact with the ActiveX flags, and alternatively, how we can, let's say we don't want to use ActiveX at all, maybe. So otherwise, we can actually use digital I/O to interact with their programs. And if I opened up my next thing, I know you're not going to see it, but I have wired here a 6525 from NI. It's just an I/O board. And what I'm going to demonstrate is turning on I/O there that's connected to some inputs on the controller, and we're going to use that alternatively. Okay. All right, so this is the editor that's quite powerful that Trio comes with. I have a program here written in their Trio Basic. Basically, there's some setup that's there. We set up here sets up what kind of axis it is. That's a 43 is a stepper. I set up gearing on here. Standardized Excel, decel. These are the virtual flags I'm going to do that I can have access from LabVIEW. I'm using what I call the virtual register 0 and virtual register 1, and enable it. And then we sit in a program here, and that is going to run the axis 5 times, 50 millimeters each time. And then when it gets, that's when it gets a VR0 signal, it's going to be waiting for that. When it gets to the VR1 signal, it'll run absolute to 0. The one thing I do like to have here on the editor is available to me, if I can find it, is highlighting. So this is actually, I actually started the program running when I was here. I hope that's going to work for me, that I didn't precede myself. Let's get that over here. So if this works properly, when I hit extend, you'll see right here, it's waiting for VR0 to become true. So okay, and now it's waiting for VR1 to come true. When I hit retract, I'm going to set the VR1 flag in LabVIEW. Okay, and that's something that anybody can do. And just behind the scenes, I have a copy of the program here. But here is just setting up, opening the IP address and port. Then this is just basically VR0, setting it to true, which is -1, or VR1, very simple. And this can then interact with a program you write and embed in their controller. Instead, here I'm going to demonstrate doing the same thing, except using input 6 and input 7 instead of VR0 and VR1 coming out of the 6525. So similar, we're going to run the program. So these are all ways you can interact with LabVIEW very simply if you use write your program motion on their Trio Basic. And alternatively, you can write your entire program without using their basic in LabVIEW using their ActiveX flags. And we'll demonstrate some of that later. But now, What I'm going to do is go back to find a PowerPoint that was here before, I hope. Okay, so here we are. 2020, I've been working for Alliance Partners for 20 years plus, and I actually finished my last company. I started my own company, and I said, you know, if I'm going to support customers, yes, I can do this with, a low-level ActiveX, but wouldn't it be nice if I had a toolkit I could do and be able to do programs and run motion and put them together in days rather than starting from scratch. So at that point, I developed the Trio Motion Toolkit for LabVIEW with the support of both Ed and my local PowerMation to help me out with hardware setups and any questions. So that I actually worked with the NI Tools Network and released that in 2021. And presently, there's a lot of these systems that are hopefully successfully running around the world. So in the toolkit is an add-on that supports the controllers running multi-axis motion and stepper and servo applications. It's designed as a full instrument driver library with examples. It supports all the programming options we talked about previously, and with a few modifications we've tested out, and a lot of the customers are using EtherCAT with it. And then, as I said, you can purchase it through the Trio, through NI, through the LabVIEW Tools Network, and install using the VI Package Manager. So now I'm going to go back to demos. I guess I better close this down again. See. Okay. So let's say you go and you install this package, the Trio controller, and what do you get with it? So what you do is you get a library that sits in your LabVIEW and under Trio. So under instrument library, you get a Trio Motion folder. In it, you have a copy of the basic program here if you wanted to install that as a key to write your basic program. You get your examples or the VIs. You get the project. You also get a README file. This shows up at least, okay? And that tells you exactly step by step how to get all the ActiveX, Motion Perfect, and then step by step how to do the installs on your computer to set up the IPs and such. Additionally, I also have information on servo tuning that we'll go back to later. Okay, and then there's a few more things, but okay, so that's what you get with it. So how would I get to this library? So what I'll do is open, oops, sorry, just. So on your palette, under Instrument I/O, under Instrument Drivers, you get the Trio Motion Toolkit. I usually like to use the VI tree if you're familiar with instrument drivers. It's written very familiar. And there's all of your examples and all your functions. Every function is included in a demo on the in an example. So what I'm going to do here is now using the toolkit. I'm going to go back. We're going to get these out of the way. Get that over. So this is very familiar. This is now that same program now written with the toolkit. And initially you set up the your IP address. And here you'll see under extend, I'm setting VR0, retract VR1. So let's see what, similarly, that's what's going to happen here. In addition, there's a bunch of functions. You can set any axis parameters and read any axis parameters. One of my favorite is MPOS, which is absolute position. And then, as I said, retract very similarly here. So what's behind here? It's packaged. I have a copy of the program we were running here. And then the initialization here is what we saw before, but it's all now packaged for you, so you don't have to set up. Just opens up the communication. And then here, very similarly, I have set VR0, set VR1, which you're familiar with by now. I also have on the palette, there is a set VR. So you never really have to go to this level. This is just a demonstration of that. But the set VR is also a tool automatically. But let's say we want to now do everything in LabVIEW. So what we can do here is we're going to just take that one program, we're going to stop it, we're going to close the editor. It's all gone. We're going to run everything from LabVIEW now. So one of the good demonstrations I have here is jog. A jog one, here's a multi-axis jog. And this is going to be very typical of every example I have. So there's a set of parameters, the which axis, the type. Again, if you remember that, 43 is a stepper. Here I have 64,000 steps per rev. And then speeds. The other thing I'm setting up here is the absolute inputs for your forward and reverse limits. And the apparatus here actually has forward and reverse limits that I'm demonstrating, as well as a homing. And we'll look at that later, so let's see what happens here. So if I jog forward, jog reverse, and then I can do that both axes. Again, speed and all these are available for all the programs. So let's just take a look what's on the block diagram here. Uniquely on the jogs, I've created a producer consumer that handles, if you wanted to use that as a template, it's just available here. Again, the init, but then I have, here's the setup, which then writes all of these for you, doing all the, setting the accels, decels. I set up soft limits, hard limits, enables. All of this is all at a high level, already embedded for you, as well as setting the hardware enables on there. So as I said, you just need to call that with the inputs. You don't need to write any of this. It's all done for you. And then just an example here, we're going to show, let's say, the jog forward. So here's just at a high level, there's your jog routine that encapsulates the ActiveX. So the other thing on every program has full error handling. So I've created an error handler that then comes up with instructions or tells you exactly if there's a communication problem, ActiveX, hardware limits, software limits, and then on the servos, be demonstrating drive faults and following errors. So that's all taken care of for you. So that's just an example of a jog routine. Let's look at some of the other examples we have here. So, and everything is explained documented exactly how to run every one of them, how to do a setup. So every single function is included, documented as well. So here what we're going to do is show some of the other routines available to you, how to use them. Again, this is very familiar as to setting up parameters. What we're going to show you here is a home function. And here we have different flavors of home. Here I'm going to do a reverse to home, decelerate, and return creeping until I'm off of it. So let's go on the axis 1 there. You'll see it moving back, and then it's then will be at position 0. I can do that multi-axis here. The other thing I'll demonstrate right here is a move relative. And I'm going to set a little higher speed here. Move relative, -10. And then I'm going to do -10 again. And here I have a soft limit set at -15. So right here it tells you exactly what happened. It was a soft limit on that axis and where it occurred. So everything's picked up for you. Then I can, as I said, here I'm going to do an absolute move forward to 100. I can actually change speed on the fly. All of this is very, very easy to do. I can set positions, can do those on both axes. Again, we change speed on the fly. Then we could be doing simultaneous both axes it handles. So I'll just get them back home and then let's take a look what's available for you in this example. So it is a little cluttered here, but I wanted to have everything for you available. So demonstrating how to use the home functions here, how to do set soft limits, relative moves, absolute moves, stops, absolute position sets. So all of this is demonstrated how to use it. So let's look at other way of doing things is, let's say you wanted to find an example alternatively. So we can use the example finder as well. There we go, coming up. So I'll just go search, type in Trio. And there's all these examples are also available for you. One I like to take a look at is sort of a fun one, demonstrating ratio. A little bit more of an advanced move. So right now I'm going to set a ratio. The master axis is 0, slave axis 1. Let's do a ratio 2. Let's move to 100 millimeters on the first axis. We'll see that they will move in ratio. And then we can, let's home them both again. And let's set instead, let's set the axis 1 is the master, axis 0 is the slave. Let's go, say maybe a 1.5, or that might be a little fast there, 1.5. And then you'll see that we now have the slave as the master. Again, let's just home. And there's other examples on doing secret moves and things I won't be showing you here today are included. So behind here, in addition to a lot of the other things you're familiar with, it includes not only how to do ratio, but just as importantly, how to unlink the axes after you've done a ratio. So, okay, so say, excuse me, I'm not doing a stepper, I'm going to do a servo. Well, these controllers are extremely flexible. So what I'm going to demonstrate right now is I'm going to turn this stepper off. I'm going to replace wires. Give me a servo connections here for their encoder. So let's see, I just seem to have lost my camera here. We don't want to do that. Okay. So let's open up a servo program here. It's going to be fairly familiar, but okay, we don't need the whole thing there. Again, very familiar with setting up the IP address. A lot of the axis setup is similar. This is a 44, which is a servo with a encoder feedback. And this is the codes, the Trio code would be 44, 8192 steps per rev. Again, setting up positions. But additionally, we are going to be setting up the position loop gain, which here we have the proportional gain, differential, integral, and feed forward. There are other things you could add to if you want to. These are the ones I'm going to be setting up here. So when I run this, now I'm going to be using the encoder that's on the motor has a marker on it. So we're going to creep until we reach that marker. Okay. Of course, I do need to add power to the Trio. It's so let's see if we're going to talk to it. That sounds better. Okay. You do need to have power on to communicate. That's a given. So again, we're going to try and do a home here. And you'll see that marker on the top. I just have a piece of tape as that's where the marker is on the encoder. So that's a different kind of homing that's available to you. We could go the other way forward to the marker 2. So here we're going to just do a relative move, minus 10 revs, or a absolute move to a minus 100 revs. And you can see that value here under MPOS, the absolute position. And very close. We'll show you how to get that tighter later. The other things that we can demonstrate here that I'm going to show you how to do is how to handle drive faults and following errors. So I actually have an input into the drive itself that forces a drive fault, and it will communicate back to the Trio that there's a drive fault. And again, all the error handling is here. It then communicates with you on that a drive fault has occurred, and I'll give you recommendations on how to clear it. So make sure I turn that off, and here I'm going to clear it, and I'll demonstrate how that's done. The other thing we'll demonstrate here is how to create a following error. So I'm going to force in 250 revs per second, which I know the drive can't do. So I'm going to write that value. I want to get a warm fuzzy here that I did write it. So yes, it read back from the controller that the speed is at 250. So let's try and do a move and see what happens when we try to drive that fast. So I move. I'm going to force it to 0 position. I was at 100, trying to go to 100. It's not going to go anywhere. And right here it comes back, shows we've created a following error, all explanations, and gives you, again, recommendations on how to clear it. So I'm just going to, we've just cleared that, so I'm just going to, let's home it again. So let's take a look at what's behind the scenes in this routine. So again, a lot of this is familiar, homing moves. But in addition, here is showing you examples of step-by-step how to clear a following error and how to clear a drive fault. So this is all sort of given to you as to good recommendations if you need to embed these in your system. So, excuse me, the last thing I want to show you is sort of very powerful. And this is one of the attributes I really like about Motion Perfect. Is they actually have a virtual oscilloscope that's available. And what we're going to show is I have a couple of tuning routines. This is a position loop routine. If I pick that up, here we go. So let's sort of get the other things out of the way here. So what I'm going to do is actually, first thing, and this is all included some instructions in the README file on how to do tuning as well. But the oscilloscope, I want to do a setup here, and I include in the folder how to set this up. And I prefer using the Tune M-Speed tune-up, which is included now. That's all the parameters here set for looking at M-Speed. So what happens in this routine is I'm going to input a square wave, and then we're going to, the Trio controller will capture that when I give it a trigger and feed it back and display it on the scope. So let's give that a shot here. I'm going to do this relative move here that allows you to define your square wave. And right here is an example of the feedback. So if people have tuned before, you know that could take some time and need some tools. It's all in here. So let's show one of the things here that I'd like to change is you'll see some dither in the motion. One thing I would like to change is the I gain, the integral gain. And through experimentation, I've played with this a lot. I know a point of 0.1 is a good one, so let's just write that in. And you'll see we pretty much removed all dither here. The other thing that I've played with, I know that the differential gain works well if I put a 2 in here. Again, this is all through using these tools to do it. So I'm going to reset the device. We're going to run it again. You'll see we have a much nicer square, much better tuned. Give you a little feel of what we can do untuned. Let's say I put a 1.5 in on your, for your proportional gain. Let's reset the trigger. Try again. You see, that's probably not what we want to do. We're a little hot here. Instead, let's give it a 0.5. Reset here. And you'll see we've really softened out, probably undertuned. So let's see a little bit what's in the background here and a lot of other familiar parts, but right here, we actually have a function available that sets and synchronizes the trigger with the, by using this, you can then synchronize with the oscilloscope and the Trio controller to do the capture. So that's all here. So here's an example how to actually set that up and tune. So that's primarily what I wanted to show you from demos. Today, I'm going to see if I can find my PowerPoint again. Okay, so let's say you're interested in finding the toolkit. You would then go to your Tools tab on your palette, look for LabVIEW add-ons. It would then take you to the Tools network, type in Trio, and then need to go to the products manual for a full licensed, select the Motion Control Toolkit, and there you can download it from there. So that's pretty much what I have to show you today. If you have any questions, please ask Ed and myself. Also, we will have all this equipment sitting out there. If you want to play with it, you're welcome to ask us any questions, and Ed can talk anything about the capabilities of the controllers at the same time. So any questions here?
Is there, can you run it with force feedback instead of position?
Yes.
Okay.
Short answer is yes. And I would assume it would be like a 10 volt, plus minus 10 volt signal kind of a thing, feedback. Like from a force transducer.
We would either give feedback in line of where we see our position based on our encoder, or if there is something that we could do direct with what's there on their position.
Okay.
So basically using like a load profile.
Right.
So doing force feedback on the drive, or doing inertia as like a negative force feedback, driving against it or with it.
Yeah, what we've done with this type of controller is there is an axis type. When he kept talking about 43 and 44, that's an axis type to us. We have an axis type that does an analog voltage loop closure instead of an encoder. So you can do it all locally right on the unit itself.
Okay.
So it's pretty straightforward. We've done pneumatic closed loop, hydraulic closed loop, really anything. So, thanks.
Thank you.
I mean, it's basically just choosing, instead of 43, the proper number for that feed. So you say 43, 6, there's a lot of different ones you can use. It's just choosing the right number there, throw that in, and you're good to go. Any other questions here?
Yeah. I think you said that only a subset of the functionality was available through ActiveX compared to EtherCAT. I'm wondering what additional functionality you would get if you were using the full EtherCAT library.
Any of the 1,300 pages of the manual, any of those functions can be run through the toolkit. There's a function here that will run a basic. It's called a run basic program. Could show you if I think we're closing on time, but any function available can be run in the toolkit by just using that low-level VI. So as I said, the ActiveX has a limited number that are available, but I've been using, even to run this, so if I need to go to one of their basic functions, I just run that instead.
If I can show. Yeah, so there's a whole pile of move absolute, high-level commands that you can fire over. There's also a catch-all command called execute, and that execute call will let you call anything that would not necessarily be or could be missing out of the OCX. So it's really, you can get anything at that point. Anything else?
So right here is the execute basic. You just tell it what, you formulate the command from the book and run it.
So he's already implemented it there.
All right. Well, thank you very much, guys.
A special thanks goes out to Kevin Chyrie, Quentin Q. Aldridge, Mark Balla, and Jeff DeVore for their help in filming. And of course, this GDevCon NA 2023 wouldn't be possible without all of our sponsors. Thanks.